So welcome to KMUTNB Colloquium 2020 organized by TGGS. First agenda of today is opening speech by Professor Dr. Somrak Chantharapon. Please.
Good morning. Good morning, Professor Apinunt and ladies and gentlemen. And on behalf of King Mongkut University of Technology, North Bangkok, it's our pleasure to welcome you all again to KMUTNB and also to our Colloquium. I think. This event is held annually, and I think it's very nice to have this kind of platform since we will have a nice opportunity for the graduate students to stimulate themselves and also to prepare their work and to present the progress in this platform. And then we can share together with your friends from the same departments and from other departments. And we also have quite a good commentators here who can give you and guide you about the direction of the research. And usually, in every time we have this colloquium, we will invite the expert from industry to give us our wisdom and direction of the recent industries. And in this time, it's our great honor to welcome Professor Apinunt from Semiconductor Technology to give us the wisdom and direction and the idea about the semiconductor industries. And I do hope that all of this event will be beneficial to you all. So finally, let me thank very much for the organizer, the TGGS, the dean, he is here, and also the lecturers and the organizing staff to organize such a nice event today. So thank you very much, and let me declare the opening of the colloquium. Thank you.
Thank you very much, Professor Dr. Somrak. Next, I would like to invite Professor Suramet to come and talk to present our guest keynote speaker today.
Okay, good morning, everyone. So, graduate students and bachelor students. So, if you watch news today, especially in Thailand, I think it's around the world, it's the same. There's one technical word that you have heard many times. It is semiconductor, right? And you might have heard about companies like TSMC or NVIDIA, yeah. And today you will experience firsthand about one of the most amazing journey in semiconductor industry in Thailand from our guest speaker, yeah. So we are honored today to listen to this kind of journey and the way in the future from someone who has been both in the academic research world as well as in the industrial world. So please welcome Professor Apinunt Thanachanayanont.
Full screen. Okay, good. Good morning, everyone. Thank you, Professor Somrak and Professor Suramet for the introduction. Right, okay. I'm very honored and very pleased to be here today to give you a talk about semiconductor industry around the world and what's possible for Thailand. Before I begin, I would like to know the background of the audience a bit. So how many of you have electronics background? Okay. Okay. What field are you in then? Mechanical engineering or chemical engineering or whatever? Material science? Mechanical science. Okay. Mechanical engineering? Okay. Any chemistry? Chemical engineering. All right. Okay. Okay. So what I'm going to do is, can you see this? Can we dim the light a bit? All right, okay, that's better. Okay, so I've decided to divide my talk into 3 parts. Okay, so first part, I'm going to give you why semiconductors are important and what are the application of semiconductors. Second part is I'm going to give you an update about semiconductor industry around the world, its value chain, its ecosystem, and what parts Thailand have been playing in this ecosystem. And the third part, I'm going to give some of my opinions on the opportunities and challenges for Thailand if you want to get more of the semiconductor pie charts. Okay, and hopefully at the end I'll give you some concluding remarks. Okay, good. So global semiconductor industry. Hopefully everyone knows that semiconductors are a very crucial, very essential parts of our everyday life. They are everywhere. So basically, if you imagine you can't live a modern life without electricity, I believe it's the same as semiconductor as well. Okay, you use it every day in your life, your mobile phone, your refrigerator, your computer, your air conditioner. Okay, and even more than that, it's very important for the emerging economy, so like digitalization, healthcare. You see more and more electronics and integrated circuit being applied to healthcare and wellness industry as well as your cars, your vehicle, automotive. You see the rising or the emergence of electric vehicle, autonomous vehicle. Semiconductors play a very, very crucial role in those industries as well as the security industry like defense, cyber security, for example. So I cannot stress enough that they are very important for our modern day life. Okay, so hopefully you agree with me. Right. So it's been very important for the past 60 or 70 years. You can see on the, press this, right? Okay, on the left-hand side of me, you see the industry since the 80s until up to now. The industry has been evolved and developed in several cycles. Like the first cycle is personal computing and mainframe computing, personal computing, and then mobile computing, internet. And also we getting into the social network industry, and also in the future we probably get into like bioengineering, cyborg, humanoid, robotics, stuff like that. And semiconductors still going to be very important to those industry. Okay, and if any of you interested in the financial stock market, I can show you in the chart on the left that the top chart is the index of semiconductor companies. The bottom chart is S&P 500. Okay, you can see over the past 10-20 years, the growth of semiconductor companies has really outperformed the S&P 500, which is the general more kind of old economy business. So you see that it in business wise giving you good return as well. Right. So more on that. Now in 2024, the net worth of semiconductor device industry around the world is around $670 billion, and you can see on the chart here that it's the foundation of the tech industry, which is they estimated to be worth around $6,000 billion. So the tech industry includes the industry, the communications, the automotive industry and other industry as well. So, and on the left, you see that today, the biggest company by market cap is NVIDIA. I guess you heard about NVIDIA, right? So it's the biggest net worth in terms of market capital in the world, around almost $4 trillion. And it's a fabless semiconductor company. I explain more about fabless semiconductor company later on. So basically, it's a semiconductor company that provide GPU chip for all the data center on all the AI. It's the backbone of AI. Okay. Right. Okay. So if you look at this chart, it's more classify the global semiconductor industry into the device segment and also the application segment. Okay. So let's say from the device segment first, it can be broadly classified into three big segments. The first one is logic. Okay, that's the biggest part of the pie. About 40% of the revenue from this industry belong to logic. So that's including CPU, central processing unit, microprocessor unit, GPU. So all the microchip used to for computation. Okay. The second part is memory chip. So it's the chip that's used in your data storage. You know, the SSD drive, your USB drive, and also it used a lot in data center as well, because after you compute, you have to store the result or the data. Okay. And that's about 30%. And the final one, as third part, is called, it's a mixture of power devices used to power, for example, your electric vehicle, and analog part, and also optoelectronics and sensors. Okay, this is the third pie of chart is also around 25 to 30%. Okay. And you can see that different product segments are used differently in different applications. For example, if you look at the computing industry, it uses a lot of logic. Okay, the majority chip uses logic and memory. While if you look at automotive or medical, okay, a lot of chip uses power devices, analog and sensor. So each different segment have purpose for different kind of applications. Okay. Okay. The final thing I want to explain on this chart, and will be elaborate more in further on, is maybe later. Okay. Anybody have heard of Moore's law before? Okay, not yet, so I'll leave it until the next slide. Okay, so that's the overall picture of the global semiconductor industry. Of course, if you look forward, okay, in the next 5 years, it's been projected that the global semiconductor industry is going to grow as much as 6 to 9% average per year. So it will probably reach around $1 trillion in the year 2030. Okay, and it's been driven by the mega trend of AI, Internet of Things, electrification, like you try to electrify everything. Put battery in your car, put battery in your blower, everything. Okay, so you want to electrify everything, and digitalization as well. Okay, so those going to demand more and more semiconductor chips. Okay, so I'll leave you this chart to study, but basically the main driven factors are the application of artificial intelligence and also Internet of Things technologies. Right, okay, so you can see the opportunities, the outlook of 2030s are also, different focus for different semiconductor chip as well. So if you in your company, if your company is into logic, GPU, CPU, MPU, you're going to be focused on data processing and communication. So those chips will be used in data center, AI applications, and so on. Wow, if you are in memory, the focus will be the same as well in data center and for communications. So the size of the bubbles here are the size of the value or target market for different applications. While if you're into discrete, analog, optoelectronics or sensors, those are going to be used a lot more on communications and automotive and industrial applications. So you can see that different semiconductor companies have different focus. Okay, you don't need to be the same. You don't need to play this in the same market as the big guys like NVIDIA, Intel, Infineon. Okay, you can, if you are small like Silicon Craft, you can play in a different niche market where they are probably neglected by the big guys, and you can still grow. Okay, so that probably will be the main message of this chart here. Right, okay, now we're getting back to the history a bit. So for those of you who are not in electronics, this is the guy, oops, sorry. This is the guy who names the Moore's law, okay? His name is Gordon Moore. Gordon Moore is the co-founder, one of the co-founders of Intel back in the 1960s. Okay, so in the 1960s, around 1965, he published a paper, and in the 1960s, it was the early years of semiconductor. It's the birth of transistor, which is the main devices for semiconductor. It's around 1945, so it's very, very early for semiconductor. He published a paper forecast or estimate that the number of transistors, which is the device in your chip, will increase at a rate about 2 times every 2 years. Okay, so that means you can put more number of device, more number of transistors, double the number of transistors in a chip every 2 years. Okay, and the development of semiconductor has been followed more or less along his prediction. So after a while, they gave him the name, well, he gave him the name the Moore's law. Okay, so that's called Moore's law. Oops, sorry, Moore's law. So this chart here is the number of transistors, and on the x-axis is the year, right? So it's been projected to increase about 2 times every 2 years, and those are the numbers in the microprocessor. So at the moment, we can probably put around 500 billion transistors in one chip, in the most complex chip like GPU, CPU, or very high density memory. Okay, but it's not about putting more number of devices on a chip, because in business-wise or business term, you want to maximize the profit. So you need to lower the cost as well. So the benefit, one of the key benefits of putting a more number of transistor devices in a chip is that you lower your cost. Okay, so the cost of a chip, okay, the cost of your CPU has more or less decreased by a factor of 2 every 2 years as well. Okay, so I think that's the main reason that's been driving the technology development in semiconductor industry for over past 50 or 60 years. Okay, because you cannot just do technologies without making money. That's not going to work, right? Okay, so a bit of semiconductor technology. Okay, so this diagram shows the year since the 1980s to probably around today, and on the y-axis is the what they call the technology node, which is more or less mean the minimum size of the transistor you can build. So in the early 1980s, we have 3 micron technology node. So the smallest transistor size that in the 1980s is around 3 micron. Okay, so you may wonder how big or how small 3 micron is. Okay, the diameter of your hair is around 100 micron. So probably about almost 100 times smaller. Right? So over the past 50, 60 years, okay, we have been follow Moore's law, decreasing the size of the transistor. Around 2000, there's a major shift. Okay, companies have been fabricating semiconductor chip on what we call silicon wafer. Basically, it's like a compact disc. Any of your generation have seen compact disc? Yeah? All right. It's very similar to compact disc, and you put fabricate chip or transistor onto the what they've called silicon wafer. Okay, before 2000, they used about 8-inch wafer or 200 millimeter wafer. Okay. The shift around 2000, company has been moving to 12-inch silicon wafer or 300 millimeter wafer. The reason is, of course, cost as well. Okay, if you can put a lot more chip onto the same wafer, when you fabricate the chip, you get more chip. That means the cost per silicon chip is lower. Okay, so that's one important shift. And then there are major technologies development along the way as well. For example, they changed or they modify the silicon substrate so that the device can perform better, faster, with low power consumption. That's the key. So the Moore's law or semiconductor technology development has really been focused on digital computational processor or CPU or MPU, because as you've seen for the past 40, 50 years, our computers, our notebook have been performing better and better, faster and faster, and using low power. So I just want to make, if you want to get away, take away from this slide, is that the Moore's law has allowed us to continue scaling down the device to allow high computational speed and low power consumption. Okay. Now, another major shift in device and technology occurred around 2015, 2014. Before that, the transistor has been built on what we call planar structure. Okay, so planar structure, basically, you like kind of have two-dimensional device. Okay, so the transistor structure is something like this. So it has 4 terminals, gate, source, and drain. And after 2015, they moved into a transistor structure called FinFET. Okay, so basically, it's kind of like a more three-dimensional, yeah, as you can see from this photograph here. So it allows better control of the transistor or the device. Okay, high speed, low power consumption, as I mentioned. And nowadays, if you talk about the state-of-the-art technology, 3 nanometers, they use gate-all-around, GAA, gate-all-around, even more, you know, three-dimensional, as you can see here. So again, to increase the performance of the device. So nowadays, you can see that the device size is very, very small. The state-of-the-art commercial technology nowadays is 3 nanometers. Okay, and we probably going to reach the end of the scaling down soon, because the physical limits or the size of the atom is around 20 angstrom. Okay, so I'm going to talk a bit about how we're going to progress if we near the end of Moore's law. Okay. Okay, now you can see that these are all the technology nodes available today. Okay, I just want to say that people sort of classify the technology node into two big groups. Okay, they use around 20 nanometers. So the technology that is smaller than 20 nanometer is called advanced node. Okay, they use in GPU, CPU, very high-speed processing, advanced node. And the technology nodes that are bigger than 20 nanometers is called mature node. Okay, mature nodes. They are still being used a lot in industry today. Okay. Right. Okay. So, and okay, now we can get to more and more than more. So the technology development for semiconductor has since been separated or diverged into two main paths. Okay, the first path is more. Okay, they call it more by making the device smaller and smaller, as I mentioned in the previous slide. So going down this path, they try to make the transistor smaller, okay, by changing the structure, changing the material, changing the way they built it. Okay, and if you're going along this path, then you can need a lot of investment. Those kind of investment, like TSMC, when they build an advanced fab, they probably need $30 or $40 billion. Okay. Now the second path is called more than more. Okay. More than more means you don't want to scale down the device, but you want to add functionality into your technology. Okay, so functionality means you want to add power device that can handle power, a large voltage and power. You want to add sensor. You want to add optics into your technology. So going along this path, you add more functionality into your silicon chips. So you still need a lot of investment to build this, but a lot less than if you go down this path, right? So the semiconductor fabrication factory then can decide which path they want to focus on, right? Okay, so that's probably the end of the first part. Any questions so far? Feel free to stop me if you have any question. Yes?
In the early slide that you mentioned about we can choose some niche market for Thai industries. And as for your case for secondary craft, what kind of application that we choose to focus?
Okay. Overall, in the big picture, silicon craft are in this part of the segment. We are in analog and mixed signal industry, which our focus is even narrower than this big part. So we focus on industrial segment here. So we specialize in what we call radio frequency identification chip. So those are used in, for example, animal farming, animal identification, industrial automation. Okay, our chip have been used in semiconductor fabrication as well, because all the factories are now highly automated. So they need to track the parts that moving around the factory. So, and also used in access control, automotive access control, for example. Yeah. Thank you. Kap.
Can you give some comments regarding this kind of development that semiconductor will be more and more involved with our life? What does it actually mean to the younger generations, and especially also for the people who are not directly in the field of electrical engineering, but maybe material science, chemistry, or even biology? So what is the future, their future that are related to this kind of development?
Okay, if I understand correctly, you mean future career as they are students, right?
Yes.
Okay. So you may think that this is all electronic or electrical engineers, but it's totally not, right? The semiconductor require a wide range of technical expertise, chemistry, material, mechanical engineering, control engineering, basically all physics, and basically all I think all kinds of engineering and science are very important to semiconductor industry. You may not see that in the design part, but you may see you see those in the semiconductor fabrication, because fabricating the semiconductor chip or devices require knowledges in material, physics, chemistry, mechanical engineering, automation engineering, control engineering. So if you're interested to get into semiconductor industry, all of you who sit here in this room can, of course, take part or be part of the industry. Biology, that may play a part in the near future, because there are a lot of research now going around the world that trying to apply semiconductor or electronics to biology as well. So semiconductor chips now can detect DNA, can detect all kind of this virus, bacteria. So I believe within the next 10 years, those applications going to be commercialized. So yes, very much part of the future semiconductor industry. All right, thank you. Okay, now second part is probably dive into more detail about semiconductor industry ecosystem and value chain, and see where Thailand stand in this value chain at the moment. Okay, so first of all, you probably need to understand that there are three main parts in the journey of semiconductor microchips. Okay, the first part is design. Of course, you need to design the microchip according to the requirements. the specification that your customer want or the product that you want to sell. Okay. The second part is after you finish your design, you send your design to manufacture. So it's manufacturing. This is the called semiconductor fabrication. So you fabricate or you build your design. Basically, you take your design and build it onto what I said they've called silicon wafer, right? And after you finish building the complete the fabrication, you send to the back end, or they've called it assembly and test and packaging. Okay, so in manufacturing, there are two subparts: the front end, which is wafer fabrication, and the back end, which is assembly, test, and packaging those silicon die. And then you have a IC product looking something like this, which will be put in your electronic products, every electronics product. Right, so that's the overall picture of the process of semiconductors. Okay, now according to those processes, the semiconductor industry in terms of business model has been classified into two different parts. Okay, the first part is are those companies who do it all. Okay, they do design, they do manufacture, they assembly and test packaging themselves. These are called integrated devices manufacturers. So these companies are the big guys like Intel, Samsung, Infineon, NXP, ST Microelectronics. So these are the big guys who do everything themselves. Okay. Now the second model is more specialization. So there are companies who do design only. This is called fabless semiconductor company. So these are like NVIDIA, Silicon Craft. Okay, so they design only. And then after they finish their design, they send the design to the semiconductor fabrication plant or factories. These are called foundries. So this company only manufacture. They don't design. Okay, so these companies are like TSMC, the biggest one, Global Foundries, SMIC from China, for example. Okay, and the third part is the assembly, test, and packaging. Okay, they're called OSAT, or outsource assembly and testing. So again, they only do assembly, testing, and packaging of IC chip. You probably less know about this. The biggest one is Amkor from US, and then ASE, I think it's Taiwanese. Okay. Okay, so these are specialized model. So each company focus on what they do best. Okay, and there are also supporting infrastructure that need to be incorporated as well. So design, they need to use software. So electronic design automation software, or EDA software. There are three big companies: Cadence, Synopsys, and Mentor Graphic, which is now Siemens, I think. And those companies, and then companies that provide intellectual property core, the IP core. Basically, it's the design Lego. So if the fabless company don't want to design parts of the chip themselves, they can buy or license the IP core from these companies, like ARM. Okay, Synopsys also provide IP cores as well. Okay, and in the manufacturing, you have material suppliers. Okay, so the wafer, the blank wafers, and also the materials and gases used in the foundries. and also the equipment for testing and assembly the microchip as well. So those are the big jigsaws in the semiconductor industry, and those chips after finished they go into the end application market segments. Okay, now there's not a single place in this world who can do all this in one country. So it's really a global journey. So for example, design might happen in US or Europe. Okay, so design might happen in US or Europe who use EDA from a US company. Then they send the design over to probably Asia, East Asia, Southeast Asia to build the chip. Okay, so manufacturing happens a lot in East Asia. After that, of course, they have to buy equipment and material from Japan, Korea. They are very big in materials and equipment suppliers to semiconductor industry. And after manufacturing, the chip gets assembled, tested, packaging probably in Southeast Asia, Malaysia, Thailand, and Singapore, for example. Okay, so it's a global journey for typical global journey for semiconductor products. Okay, so now if you look at who plays a big part in different value chains, the EDA and core IP, mainly US and Europe. They're very, they dominated this segment. Logic, also US. As you can see, NVIDIA, Intel, AMD, all US company. The discrete analog and optoelectronics now in Europe and I think it's Japan, right? Play more part in the discrete analog and optoelectronics. Memory chip, about 60% come from Korea. They are Samsung, SK Hynix are very big in memory chips. So you see that US, Europe, Japan, and Korea play a very big part in design. For manufacturing equipment, US also have a big part, Japan and Korea. Materials and wafer fabrication more now in Taiwan, Japan, and Korea. And China also gaining ground. And assembly, tested, and packaging. Now this happens a lot in Taiwan, China, and Southeast Asia. Southeast Asia hold about 20% share in this market. Okay, so overall value chain, US is still about 40%, quite big, pretty big. Okay, and they are now watching or try to control the growth of China, as you probably heard over the news over the recent years. Okay, so that's the picture of the value chain. Probably not going to spend much more time on this. So the chip, as I mentioned, where the chips design mainly in the US and Europe, okay, for logic chips, and for memory chips, then they are designed in Korea. What about fabrication? There are totally about 1,500 factories around the world. That's still a lot in US, North America, but the advanced node semiconductor fabrication are in Taiwan and Korea. Okay, advanced node, I mean less than 10 nanometers. So if you look at the technology node here, you can see that the advanced node less than 10 nanometer is only two countries can do at the moment, Taiwan and South Korea. And last thing I want to mention on this slide is China is gaining ground on the mature nodes fabrication. They're building a lot more, several mature node fabrication plants. And you may have heard the news over the past few years that the SMIC can now do 7 nanometer technology. Okay, so they are catching up to the US and Taiwan. Okay, now the ATP part. Okay, ATP part, the assembly testing and packaging still happens a lot in Taiwan, China, and Southeast Asia. Those are the 3 big players in this ATP part. And if you zoom in to the Southeast Asia, you can see that this is the projection. This is 2022. China is around 30%, and Southeast Asia around 20%. It's been projected to grow to 20 to 20% in 2032. And if you zoom in further into that, you can see that Thailand is here. All right. At the moment, it's around 1.5 to 2% share. Sadly, it's been projected to get less to 1%. Okay, and this is because the projected growth of other countries, neighboring countries like Malaysia and Vietnam, they're projected to be gaining growth. So this is not good, right? We have to do something. Okay, the Thai government and all the have to work with the industry and academic institution to do something to try to fix this. Right? We don't want to be smaller. We want to grow, right? Okay, so that's kind of a quick snapshot of the current situation in the ecosystem and value chains. Okay, any questions? Have about 10 minutes left. Okay, I'll try to speed up. Okay, now, okay, so why now? Why now? Why semiconductors now? Because you see that over the recent year, that situation of chip shortage after COVID or during COVID, and also the rising tension between US and China trade war, right? So US trying to birth control China economy, China technologies. As you see, they backlist Chinese company from gaining high technology equipment, high technology chips. Okay, so it's not about it's not only about technology now, it's about control as well, right? So over the past few years, you can see significant investment, significant growth of investment in semiconductor, much more than over the past 20 years. So this is the new big wave of semiconductor investment. And it probably, in my opinion, will be the last chance if Thailand wants to get a big pie chart of this industry. Okay, so we have to do something and do something fast. Okay, so this chart you can look it up later. Then investment of semiconductor fabrication around the world, focusing in Asia, Europe, and USA. Okay, now zoom in into ASEAN semiconductor industry. It's been growing, right? So this is the semiconductor IC part. So the value has been growing into around $500 billion in 2023. So if you look at the countries, the number one is Singapore, second one Malaysia, Philippines, Vietnam, Thailand down here. So we're still like number 5 in ASEAN. If you don't count Laos, Cambodia, what else? Brunei, be probably the last. All right. So it's it's not a very happy situation to be in. I think we have to improve a lot. Okay, so I kind of do some of my homework and summarizes the investment in semiconductor over the past few years. So quickly, there are major investment in Singapore and Malaysia in both semiconductor fabrication and ATP and also design. Okay, minimum investment in Philippines and Indonesia, which is good, but quite a lot of investment in Vietnam, as you are probably aware of. The investment of ATP facilities, not fabrication plant yet, but I like to point out that Marvell is a fabulous semiconductor company, has announced that they will invest in design center in Vietnam. I think that's kind of a trigger, alarming that Thailand has to do something to attract those companies to invest in Thailand. Okay, we attracted some. For example, Infineon has announced to build a new wafer testing plant around. They said the investment will be around $1.7 billion. Sony, which do I think it's optics, opto sensor, optoelectronics. Okay, and Infineon again. Maybe this is a mistake. Sorry. That's it. And then we attract a lot of investment in PCB and PCBA companies. So companies from China, Taiwan comes to build their PCB, PCBA factories a lot in Thailand, which is okay, but it's not a high value added industry. So the profit margin in February, a single digit profit margin, very, very slim. So I think we need to do better than that, right? Okay, so if you look at, I borrowed this chart from TMAC, right? So we have a lot in PCB, PCBA, which is at the end of the product. We have a lot in ATP, OSAT. We don't have wafer fab. We have TMAC, which is okay for sensor research and fabrication, I think. We have very few design companies. Silicon Craft itself, Design Gateway, Nishinbo up in the north, and Rome Semiconductor, which these two companies got their work from their mother companies, right? So that's the current situation. So what are the opportunities for Thailand? ATP, fabrication, design, or we do everything? All right. So I'm going to try to break it down. Let's look at the value added first. As I mentioned, 3 parts, right? Design, fabrication, assembly, and tested. If you look at the value added down here, design have about 50% value added. So basically, if you your product is 100 baht, right? 50% is your value added, 50 baht is your value added. So very high value added. But also you need a lot of investment because it's an intellectual property in designing chip, high performance chip, right? Manufacturing value added is down a bit to around 25-30%. Okay, and very heavy investment, capital expense, a lot of cash need to build a large fabrication. Backend, very slim value added, at most 10%. All right, so medium capital expense. So now do you see the value added in the value chain? So you can think, where should I play? Where should we play, right? Okay, so Okay, so it's follow the smiley chart, right? So this is value added. This is design, manufacturing, and end product. So we are Thailand industry is down here. So some people call we are trapped down here. So we how we can move up the stream or to the product stream where you have more profit, more value added. Okay, so first ATP, we are good at ATP. We have a lot of number of OSAT. What can we do? Can we strengthen them? Okay, can we give them muscle strength? Okay, if you look at the assembly and test process, basically this is the basic process. After you got fabricated silicon wafer, you need to check them, dice them into small silicon die, and then put the silicon die, attach them to some packages, right? And then test it, and then after tested, you ship to your end customer. Okay. If you look at packaging technology, it's been since the 1940s, 50s, right? We have conventional package that you still use today, wire bonding, flip chip, wafer level. Now we have to get into what they've called advanced packaging. Those are 2.5D, three-dimensional packaging where you can put different functionality chips like logic, memory, sensor onto the same package, right? So these are the high value packaging. These are used in complex chip like GPU, CPU, right? Now, if you look at the potential market, you can see that the market for packaging is going to be 50% for advanced packaging. So the growth part will be in advanced packaging. So that means we should try to develop our OSAT or ATP companies in Thailand to gain capabilities in advanced packaging. Okay, because those will give you a higher value added. Right. So just a key takeaway from this slide is I think we cannot leave the OSAT companies in Thailand to stay where they are or to dry out where they are. We need to improve them. And those going to require technical knowledge from probably you guys who sit here in this room. Okay. Well, I put this slide to explain a bit why we need advanced packaging, right? So I'm going to go through it quickly. As the complexity and number of transistors in chip grows, okay, the die size of the chip grows quite big. Okay, it can be up to several hundred millimeters square. Okay, for example, if you look at this silicon wafer, if you have a large die size, you get less number of chip, and you usually have defects when you process this wafer. It's unavoidable. For example, if you have 4 defect spots here, you can see that the chip or the silicon die here with defect spot cannot be used, right? So here you have about 12 dies, 12 silicon chip. 4 of them are defected, right? So you all have yields of around 67%. Only 8 chips after come out can be used. But if your silicon dies are smaller, defects spot happen at the same point, you can calculate and see that the yield goes up to about 90%. Only a few number of chips get defected. So once your die size get larger and larger, your yield drops. Right? When your yield drops, that means your costs go up. Right? So once your die size is big to us up to a certain point, it does not make sense now to make a large chip. Better way people found is to make smaller chip, and put them into the same package. So you make smaller chip, smaller GPU chip, don't have to be so have so billion transistors. You have memory chip, and then you put them alongside in the same package. Those are basically advanced packaging, and those technology are used in the current GPU die, for example. Those come from NVIDIA. Okay, they use advanced packaging. Okay. What about wafer fab? Do we need to have wafer fab in Thailand? We don't have one at the moment. Okay, now let's look at the manufacturing process. Okay, the silicon wafer go through a number of processes, right? Building layers by layers. Okay, there are basically 4 main processes in semiconductor fabrication: oxidation, coating, lithography. Basically, lithography is putting patterns on your silicon wafer, etching by your chemistry know etching, right? Etching away the materials, and the doping, all right? Okay, so now if you want to build a wafer fab, let's look at the cost to see if it makes sense. For advanced nodes, right? You can see that this is the cost of wafer fab construction. This is the size, the technology node size. 65 nanometers cost probably about $400 million. If you want to build 5 nanometers, it's goes up to $5 billion US dollar. All right, and it's estimated that if you want to build 3 or 2 nanometers, it's $30 or $40 billion. I think we can forget about that for Thailand. Don't you think? All right. So obviously, advanced node is not something we want to do, right? We can't do. If we want to have a fab, we need to look at mature nodes, more specialized nodes, boutique nodes, right? And the fact also said themselves, other countries cannot invest too. The only one who can invest is TSMC, Intel, Samsung, the big 3 guys. You can see that this is the number of wafer fab by technology node. There's a lot of wafer fab offering for 130 nanometer technology. There's only 3 companies offering 10 nanometers node and below: Intel, TSMC, and Samsung. Right? So if you want to have a wafer fab, look around here, if there's still opportunities. Okay. Okay, so there's still plenty of demands for mature nodes, as I mentioned. Around 60 or 70% of values are still in the market are still from mature nodes. Right? Okay, this chart may be too small, but basically say how each market, what technology nodes are used by each market. So mature nodes are still used a lot in industrial, telecommunications, consumer, and automotive segments. Okay, now for example, automotive industry. Now there are a lot of semiconductor microchip in cars now for driving, for controlled driving, MCU, for sensor, assistive driving, and so on and so forth, right? And the projection has growth as well, about 9 to 10%. So it's basically, I just want to emphasize the importance of mature node technologies. Okay, now at the moment, the majority of mature nodes are distributed almost evenly. A lot of them in China, about 30%, and about 30% also other elsewhere, which mean in Asia, in Europe, and also. So in terms of capacity, it seems to be it's not in shortage. Okay, so it seems that mature node technology is not in shortage. So should invest, should have a wafer fab in Thailand if there are much more capacity available around the world. Maybe, maybe not. But if you can see that it's projected that a lot of mature nodes fabrication plants will be in China. So if the rising tension between US and China escalated further, so the US and alliance might ban product that get fabricated in China, then there may be opportunities for Thailand and Southeast Asia to have wafer fab. So maybe, not sure, but I think it's personal opinion. I think it's a weak prospect to have a wafer fab in Thailand. Okay, so what about design? Can we do design in Thailand? We already have a few companies, right? So design, basically, design semiconductor comprises of hardware and software design. I'm going to focus on hardware design. So basically, you get product specification, you design the architecture and the circuit, and you validate your design. So from specification to schematic design, you use EDA tools to simulate this circuit, and you do the layout design, basically translating this symbol into a drawing, and this drawing gets sent to the wafer fabrication. Okay, now what can we design? Okay, what should we design in Thailand? If you want to design GPU, AI is growing, right? Can we get into GPU design? You see that people estimate that the cost of using state-of-the-art technology node, 5 nanometer, 3 nanometers, design cost for one chip, $700-800 million for one chip. So GPU, maybe not. We want to do mature nodes again. A lot of industrial application, automotive, consumer applications. We can use mature node where there are less design costs. Okay, this design cost involve the salary of your engineer, software verification, and mask cost. Okay, so and test and qualification. So we can do the design. We can focus on the design, especially for the mature technology nodes. Okay, so where do we want to play? So as mentioned, we have logic segment, memory, and DAO, right? Discrete, analog, and optoelectronics. As you can see, we probably want to focus on this segment, where there are less investment and there's still plenty of demand and application in this segment, discrete, analog, circuit, and optoelectronics and sensors. Okay, so we can focus on mature node and more than modes technologies, and I believe we can use the industry or support the industry in Thailand as stepping stone to get into the global markets. Okay, so industry that we have a lot in Thailand are automotive, right? Manufacturing, agriculture, what else? Services, right? Okay. Okay, so the challenges, coming to the end now. The challenges, the first one is we want to attract investment, right? FDI, foreign direct investment. So we have to compete with neighboring countries because we are in the same region. So when the US European company or Taiwanese company, they look at Southeast Asian as a whole, which means when they invest one facility in neighboring countries, they're probably not going to invest a similar or a facility in the same area. So we can't deny that there's a competition between neighboring countries in Southeast Asia, and I think we are a bit slow, okay, to say as a fact, because Malaysian, Vietnamese has already announced their national semiconductor strategy, maybe 2 or 3 years ago. They start attracting investment already. Okay, so and the second part is we still have, I think, lack of high skill resources, high skill workforce that tailor for this semiconductor industry. So the government and the Ministry of Higher Education are working on this, and they have a lot of good programs. They have semiconductor sandbox program. They have boot camp programs. They have what else? National Training Center program. So which is good coming along. So we are doing something on that, but I still think that at the moment they are leaning towards bachelor degrees more than master and PhD degree. So we need to develop and attract more master and PhD graduates in these areas. So hopefully after this talk today, I've convinced some of you guys to change into semiconductor industry. All right, if you still can. Right, and we're a bit late, but we're doing something. So the government and the BOI has drafted the national semiconductor industry, and I think they published a draft a few weeks ago, and they're to be announced in the early January 2026, and they're focusing on trying to attract investment around $15 billion and develop workforce around 80,000 people. So I think we are coming along the right track, more or less, but we have to move faster and show our commitment to the US, EU, and Taiwanese investor that we are committed to, in the long term, to develop this industry. Okay, I haven't seen any number, committed numbers from the government in terms of investment. For example, Malaysia has announced that they will commit about $5 billion over the next 5 years. I think Vietnam has said that they will commit about $1 billion to support their industry. So I'm not sure, I haven't heard any number from the Thai government yet. Okay, so oops, sorry, that's backward. Okay, that's probably the last slide, sorry. So I think the strategy and commitment from the government and related agency are urgently needed, and they need to be serious. And I think it's coming along. And we need to strengthen the outsourced assembly and tested companies in Thailand, industry in Thailand, to advance packaging. We probably try to attract investment or co-investment for wafer fabrication, especially in the mature nodes. But I think building up on chip design, it's relatively more easy, or relatively easier than attracting the wafer fab. So I think we should focus on that. And I think one thing that will help that we create Thailand local policy content in terms of semiconductor as well. So that will help as a stepping stone for anybody who want to start a semiconductor design company in Thailand. And last but not the least, of course, is developing high-skilled workforce that where universities and institutions come from. There need to be programs and focus on developing, especially master and PhD. I think master and PhD graduates in this area. So that's come to the end. Thank you very much.
And any question from the audience? Any question from the audience?
Good morning, Professor. So from your slide, I come to know that the defective parts, if you make with your small die, you will be getting 33%. Even though if you're going for the bigger die, it will be reaching up to 3%. So in global, everywhere they're following the Six Sigma strategy where it is of 3.4 defects parts per million opportunities. So what is the strategies which they are following in the semiconductor industry about to reduce these defects? That is my first question. And the second one is, what is about the disposal strategies which they are following for this defective products and also for the end of life products? And third one, what are the SDGs which they are following in the semiconductor industry? Because in value chain, you have put all the things about this manufacturing process. So what about this defectives are like?
Okay.
End of life products?
Very, very sorry. Can you go one by one? The first question is,
Okay, okay.
I'm a bit old now, so I
Yeah.
can't remember all the questions.
Okay. So the first question is, in the defectives, even though if you optimize the die design, if you go for the larger size of die, you will be getting reduced number of defects. Almost you made it as like 97%. Rest of the 3% will be considered as a defective products. Am I right?
Mm-hmm.
So everywhere in the global right now, they have moved on the quality things like Six Sigma strategies.
Right.
So it is saying that it should be only 3.4% defective parts per million opportunities. So what is the strategies that they are following in the semiconductor industries to reduce these kind of defects?
Ooh, probably I'm not the one to answer this because I'm in design, not in manufacturing.
Okay.
But as I can say is, you know, wafer fabrication plant is very, very, very clean already. The classroom in the class order of 100. So very, very few particles can enter the factory. So I think they're doing everything they can to control contamination. I'm not sure, to be honest, I'm not sure what other technology they have upcoming in trying to reduce the sources of defect. But I think they're doing everything they can, and if you go into the wafer fabrication plants, they are super clean. The air is cleaner than the air you breathe now. So sorry, I can't answer your question.
Yeah, no problem, Professor. The second one is like about the disposal. So the disposal of the waste material and also the end of life products of the semiconductor. So what are the strategies which they are following?
Okay, you mean talking about the waste of semiconductor, right?
Yeah, defective products and also after we consuming it, that is going to be waste, right? So because in value chain you mentioned everywhere like it is a global operating system to collecting this material or manufacturing or design or the testing and assembly. So in this case, what are the strategies which they are following for this disposal? I would like to know. That's it.
Yeah. Again, I'm in design, so you are right. You are concerned about waste, especially in the wafer fabrication plant, and the industry, especially from the EU and the US, imposes several regulation and control for those plants, especially if they established or located in the US, EU, and Taiwan, of course, they need to have proper waste management and control, because a lot of chemical gases wasted come from those fabrication plants. So yes, sorry, that's all I can say.
Okay, and the last is like right now you talked about this the opportunities in the Thailand to start out this semiconductor industry, and nowadays in this SDGs are the major things that they are following it, sustainable development goals. So what are the sustainable development goals will help Thailand to achieve this semiconductor industry?
Sustainable, okay.
Yeah.
That's difficult. I think
Because
a lot of application from semiconductors can also help sustainability goals as well. Because, for example, our microchip, RFID chip, have been used in waste management in Europe. You know, when in Europe, when you throw away your waste, you have to classify, separate into recycle, unrecycled plastic, perishable waste, right? And RFID can make sure that people do it properly. So each bin will have an RFID chip embedded into those, and when the regional government or workers come to collect the bin, they will check that. So that's probably one example. You can see that the relation between semiconductor and sustainability. Yeah. Then there are many other applications as well.
okay, Professor, thank you so much.
Sorry.
Okay, thank you very much. So I would like to thank Professor Dr. Apinunt Thanachanayanont for sharing your valuable insight into semiconductor industry, its technology development, and including opportunity and challenges for Thailand. Next, I would like to invite Professor Dr. Somrak Jantara Ampon, KMUTNB President for Research, to give the token of appreciation to our guest speaker today. Thank you very much. Next, I would like to invite everyone to join the group picture in the front, please. Or to the back. Yeah, we can do that also. Yes. So next we're gonna have a coffee break, and you can prepare your presentation for